Okay, so um, we're going to be working on 1D flows. And so so this is any first order, and it needs to be one first order ODE. So now one thing to keep in mind, as physicists, we tend to think of a one-dimensional system in mechanics when we think about one dimension. And so if we have like a spring here that's moving back and forth, we might think of this as a one-dimensional system, but this is actually a 2D system from the math standpoint.
Because you got time.
Well, no, because it's F equals ma. So
Oh,
the
okay.
second derivative of x with respect to t is minus kx. So because it's a second derivative problem, it's actually a 2D system as far as a mathematical system is concerned. So what we're really talking about for 1D system, when we talk about the dimension now, we're talking about the size of the phase space. So the phase space of one spring that's moving back and forth would be the space of the momentum and the position. So that's a 2D system.
Right.
So when we think of 1D systems, we don't tend to, as physicists, we don't tend to think there's a lot of interesting one-dimensional systems, but there are. There's models of lasers and there's models of population dynamics and things like that are going to be 1D systems. And so we're thinking here of any x dot is f of x. And what we want to learn to do is we want to learn to think geometrically about the solution. So all we can do, so it's a one-dimensional thing. So if this is the x-axis, then let me suppose that this is a plot of f of x. This curve here is f of x. Then all we can do is flow to the right or flow to the left. All right, so the one-dimensional system is just going to be represented by arrows on the axis, where I'm either flowing to the right or flowing to the left. And if x dot is f of x, whenever f of x is positive, the flow is to the right. And whenever f of x is negative, the flow is to the left. And so we see here that the flow looks like that. And it flows to the right until we reach this point. And I'm going to make this point here be by a solid dot. And I'm going to make a point here be an open dot. And we'll notice that if f of x is equal to 0, we're going to call this a fixed point. Because as far as the flow is concerned, if you started at that point, you wouldn't move. You would just stay there. And so this point here, we're going to call a stable fixed point. And this point over here, we're going to call unstable. Because if we start near the stable fixed point, we flow towards it. And if we start near the unstable fixed point, we flow away. Yay. Everybody good?
Good so
How you
far.
doing, Daniel?
I'm good.
Okay, so let's suppose that I plot f of x versus x, and I get something like this. The flow would always be to the right, but around here, I would be going slower. And over here, I would be going faster, right? Because x dot is bigger. Not terribly interesting, right? Or if f of x look like this, then we're at this point right here, f of x star is 0. At this point here, say x star. I would see that the flow is to the right always. But what I would do here is I would mark it with a half filled circle, because this is going to be what I'm going to refer to as a metastable fixed point. It's a fixed point that is basically half stable, right? If I'm coming from if I start at any initial value from the left, I'll move towards the right. If I start at any initial value to the right, I'll still move to the right. So I'm moving away from the fixed point on one side and towards the fixed point on the other side. So it's like a half stable fixed point. Everybody good?
Yep. Kind of like limits.
Yep.
Vaguely.
So basically all we're doing is we're looking at the sign of the f of x, and we can find the fixed points, and then we can decide whether or not the fixed point is stable or unstable. It's really all we can do here in one dimension. Now, an important idea is linear stability analysis. You'll notice that for any fixed point that is stable, so this is some f of x, this was a stable fixed point, that by necessity, the slope is negative. And for any fixed point that is unstable, see, I'm going, if this is my flow, right? So here's my f of x. My flow are the arrows. The f of x is the curve. If the slope is positive, I'll have an unstable fixed point. And that's because if the slope is, you just sort of graphically look at it, it's kind of obvious. So if x dot is f of x and f at x star is equal to 0, then if f prime evaluated at x star is positive, x star is unstable. And if f prime evaluated at x star is negative, then we say that x star is stable. Okay, that good? All right, so now, so one might wonder why we should examine differential equations that are first order like this graphically at all, right? So if I have x dot is f of x, then that's dx dt is f of x. And so in principle, dx divided by f of x is equal to dt. And if I integrate both sides, then I get t minus t0 is the integral from x0 to x of dx prime over f of x prime. That's the solution to the differential equation x dot is f of x, right? I mean, by almost manifestly, the way we're setting the problem up, the problem has an analytic solution. And if you wanted to find, now, it might not be very pretty. This might be ugly. And then we might need to invert to find x as a function of time, right? So normally we want to know what x is as a function of time. So we might have some ugly integral that we have to do. And then we need to invert it to figure out what is x as a function of time. Okay. So if your goal is to find an exact function, x is a function of time, then you can always do this. But frequently your goal is to understand what the system is going to do. And instead of thinking about exactly where the system is at a given time, if you pay attention to what the system's going to do, you can very quickly get all the information out that you need. So for instance, if I have, some f of x, which is x squared minus the sine of x. So x dot is x squared minus the sine of x. And I asked you to tell me what that system does. Well, you would write down, well, the integral of dx over x squared minus the sine of x is equal to the integral of dt. Okay. When you would look at this and go, ugh, right? There's nothing good to do with that. Okay. That's just ugly. Nothing particularly interesting about that. On the other hand, let's suppose I want to think graphically. So let me try to find some fixed points. So if I want f of x to be equal to 0, that's the same thing as x squared is equal to the sine of x. All right, now that's still hard to solve if I actually tried to solve it. On the other hand, if I plotted sine of x and I plotted x squared, I see that there's some point here where x squared is equal to the sine of x. I can see that that's the case. Everybody agree with that? Okay. And so I can see a little further. So if I'm looking at this in terms of x dot is x squared minus sine of x. I can see that when x is more than this x star value, that x squared is more than sine of x. And so I can see that x dot is positive everywhere. So I know that if this is 0, there's some x star over here, and that the flow is away from that point because x squared is more than sine of x after that point. And if I think about this for a little bit, if x is less than x star, then x squared is less than the sine of x. So I'm in, say, this region in here, right? So if I'm over here, right, then my blue curve is below my black curve. And so if I subtract the sine from the x squared, I see that my flow in that region is away from this point. And so I see that at that point, I have an unstable fixed point. So I can describe to you what the system does, even though I can't solve the math. So even if you can't necessarily solve the math, like you look at this integral and you're like, oh, I can't tell what the hell to do with that. You can think about how to graph the function and make some progress. And you can understand what the system does, even though you might not solve the math exactly. Good?
So to be sure, this is like only around the point like x star, right? If you were to choose like a different point, would you have to look and see what the two or what the x squared and the sine x are doing?
Yeah, so I've drawn this curve this way, and it might be a little bit more complicated than that. I'm pretty confident that if I'm doing exactly x squared, that there's not going to be any intersection of this blue curve. So once I get to the left of x star, the blue curve is going to be above the black curve. And so x squared minus sine of x is going to be positive. Wait, squared minus sine of x. Oh, there's another fixed point. Doink. There's another fixed point here. Those two curves also intersect there. Oops. See, look, see, they intersect right there. So anywhere where the two curves intersect, they are going to, yeah, that makes sense.
Yeah, that would make sense.
Okay. And anywhere to the left of the origin, the flow is to the right. Good.
Good here.
Yeah, I'm good with that.
Okay. Let's do an example. Let's try to understand how to model population growth. Okay, so let me suppose that N is the number of tribbles, and I'm trying to find out the number of tribbles as a function of time. Okay, so let me suppose that I have this as my first model. This is a bad model because the solution to this model is an exponential growth. So if R is a positive number, then N0 e to the RT, it would be the solution, and that's exponential growth, and it's not very likely that the tribbles will grow exponentially. Tribbles might, but do you folks know the reference?
I cannot say I do.
Not quite.
There's a original Star Trek episode called The Trouble with Tribbles.
Are
With
those
the
the little
tribbles.
furry things?
Yeah, the little furry
Oh,
thing.
okay, that's where I've
And
heard
they
of
go,
them. Okay.
they populate and go nuts. So that's not a very good realistic model because it leads to exponential growth. So let's try something else. If we try Rn 1 minus n over k, where k and r are both going to be positive numbers, and k is something we're going to call the carrying capacity. All right, so let's look at this example of population growth. So now, if I look at just the signs, of n dot, then we see that if n is greater than k, then n dot is negative. And obviously we need n to be positive, right? Can't have negative numbers of people. So if n is more than the carrying capacity, n dot is negative, which means the population is decreasing. But if n is less than k, see if I'm just looking at this parentheses, right? So if n is more than k, then n over k is more than 1, and 1 minus n over k is a negative number. But if n is less than k, then n dot is positive. And so in this model, we have two fixed points. We have a fixed point at k and a fixed point at 0. If I plot the model, this is n dot, is this curve. We see that the dynamics are that I drive to the carrying capacity. So this is called the logistic equation for population growth. And in the logistic equation for population growth, there's a carrying capacity, and the model drives you to the carrying capacity. So there's some, say, amount of resources available, right? So if I don't have very many members of my population, then I can grow. But once I start to run out of resources, then the rate of my growth slows, and eventually I reach the carrying capacity. But if I start off with too many people, then I don't have enough resources to go around, and so the population declines until I reach the carrying capacity. Okay. That
Good.
sound good?
Yep.
All right, so let's do to practice. Let's show that n star equals k is a stable fixed point using linear stability analysis. So f of n is Rn times 1 minus n over k. And so it's going to be convenient for me to write that as Rn minus R over k n squared. Then an f prime is df dn is R minus R over k times 2n. Right? That'd be f prime. And f prime at 0 would be R, which is positive. So 0 is an unstable fixed point. But if I put into f prime n equals k, which is my other fixed point, I would have R minus R over k times 2k. So the k's would cancel out. So that would give me minus R. And so f prime at k is negative. So n equals k is a stable fixed point. Happy enough?
Yep.
All right, so that's fixed points and flows. Now, fixed points and flows are okay. And this isn't a really big deal. But the more interesting thing is something we're going to call bifurcations. And a bifurcation is going to be a change in the system in terms of the flow or the number or the character of the fixed points. And we're going to have in one dimension 3 different types of bifurcations that we can have in one dimension. One of these bifurcations we're going to call the saddle node bifurcation. So we're going to suppose, for instance, that x dot is r plus x squared, where r is a number that I can change. So now, for a given value of r, I have a particular flow. I change r, I have a different flow. I change r, I have a different flow. I change r, I have a different flow. So for a given r value, there's a flow. Now the question is, what could happen with the different values of r? So for instance, let me suppose that I have r is minus 4. So if r is minus 4, then f of x would look like that. At r equals minus 4. And I would see that I have a fixed point at 2 and another fixed point at minus 2. So x star equals 2 and x star equals minus 2. We have some fixed points. And let's all draw some arrows on our axis to indicate the directions of the flow. So here our flow is given by x dot is minus 4 plus x squared. So we want to draw some arrows on our axes to indicate our flow. You both draw some arrows. I think in this region, the flow is to the right, because f of x is positive. I think in this region, the flow is to the right, and I think in this region, the flow is to the left. So one of these fixed points is stable and one of these fixed points is unstable. Which one is stable?
The one on the right is, no, the one on the left is,
Yeah,
because
this
they're
one is
both
stable,
flowing together.
and this one is unstable. So this one is unstable, and this one is stable.
So is this kind of why when we look at complex geometry and like fractals, is that why some of them are called attractors? Because
Yeah,
of
okay,
the
so
flow of them?
generally speaking, an attractor is a set of points where things flow towards it. So in
Okay.
this case, the stable fixed point is an attractor. It's not a very interesting attractor. It's
Right.
just a single point.
But that's kind of where this is heading, because I know
This will
bifurcation
head
leads
in those
into
types of directions in the future.
awesome. Okay.
Now, if r though was equal to plus 4, and now x dot is equal to 4 plus x squared, everybody draw the flow. All right, let's first draw f of x. What does f of x look like? Still a parabola.
Yep.
But where's
It's
the bottom
just
of it?
bottom of it is above
Up
0.
there, right? And now the flow is to the right, and we see that there are no fixed points. So as I take the parameter r and change it from negative values to 0 and then to positive values, for any value of r that's negative, there's a pair of fixed points, one stable and one's unstable. And for any value of r that's positive, there's no fixed points at all. And so let's start with it being, say, the positive value of r, and I decrease r until I get to 0, and then I keep going. So the flow changes in character. The flow used to always be to the right, but now the flow isn't always to the right. There's a pair of stable and unstable fixed points which show up. And so we have a change in the character of the flow. We have two fixed points that have been created as I go from positive r to negative r.
And then an r equals 0 would be a
That's
quasi-stable or
that is the
semi-stable.
place where, yeah, so at r equals 0, now the flow looks like this, right? So the flow would be like that again. but I'd have some sort of half stable fixed point here.
Right.
Okay.
Okay.
And r equals 0, we're going to give that a special name. We're going to call that the bifurcation point. The bifurcation point is the value of the parameter in which the character of the system changes. So we undergo a bifurcation at r equals 0. For r positive, there's no fixed points. For r negative, there's a pair of fixed points, one stable and one's unstable. So r equals 0 is the bifurcation point. And so if we want to make a diagram that we're going to call the bifurcation diagram. And what we're going to do on the bifurcation diagram is that we're going to plot r on this axis and the fixed points on that axis. No, I'm going to do it the other way around. Well, no, I think I want to do it that way. Yeah. That's what I want to do. Yeah. So I'm going to plot the fixed point on the, so I'm thinking of the fixed points as dependent on the r. So the r is essentially the independent variable. It's the thing that I'm getting to tune. And we see that if r is positive, there are no fixed points. But for r negative, there are fixed points. So here, f of x was r plus x squared. So f of x equals 0 is the same as r is minus x squared. So that's these two curves. And I dash this curve because there's an unstable fixed point at positive x and a stable fixed point at negative x. Now, the way to read this diagram is that r is the parameter that you're tuning. So you've tuned up the system to have a given value of r. So maybe r is +3. When r is +3, I think of the vertical line at +3, and I look for intersections with the curves. Since I don't have any fixed points, there's no fixed points at r equals +3. On the other hand, if I set r to -3, I have an unstable fixed point here and a stable fixed point there. So that's our bifurcation diagram. Okay. So in the saddle node bifurcation, one way to think about it is that if I think about it at starting in this spot, if I start with this graph and I raise the graph by increasing r, the stable fixed point and the unstable fixed point come together and they collide. And when they collide, they annihilate each other and the fixed points go away. This type of bifurcation, which is the saddle node bifurcation. So this is the saddle node. The other term for this bifurcation is the blue sky bifurcation. Because as you're tuning the parameter, fixed points appear out of the blue sky. Right, so they just sort of appear. Right, so there weren't any fixed points, and then there become two. Okay, that good?
Yep.
Daniel?
Yep, good.
I guess let me write it as. I'll write it as r minus x squared. Okay, so this is the normal form of the saddle node bifurcation. Okay, so the normal form is an important concept here that you start to see in differential equations and advanced mathematics. The normal form means that you might have some other system that doesn't look like x dot is r plus x squared. But near the bifurcation point, you can do a Taylor series expansion, or you can change coordinates and make the differential equation look like r plus x squared. So the idea is that there's a change of coordinates, at least locally near the bifurcation point, and near that whatever differential equation you have becomes like r plus x squared. So let's do an example of a system that has a saddle node bifurcation, but doesn't look like this same equation.
Is that kind of like with the harmonic oscillator with the
Yeah.
energy?
So in harmonic oscillator, a whole lot of systems look like harmonic oscillators near a minimum of the potential energy function. So any system that has a potential energy function that has a zero in the slope of the potential energy function, near that place, it looks like a harmonic oscillator. So the harmonic oscillator is essentially the normal form of a whole bunch of systems. And here what we're saying is that saddle node bifurcations look like the same, have a normal form that looks like r plus or minus x squared. And basically what you need to have happen is you basically need to have some sort of bowl type shape run into some sort of tangent line that then cuts across and becomes a secant line. So if I think about the system that I had up here, right? I have this bowl-like shape. I have this horizontal axis. And as I change r, I'm moving basically the bowl relative to some horizontal line. And they become tangent at some point at r equals 0. And then they cross and have two intersections. So now let's look at this system. X dot is r minus x minus e to the negative x. So let's try to find the fixed points. Well, so that means x dot is 0. So that means r minus x minus e to the minus x has got to be equal to 0. Okay, so now that's transcendental. We can't solve that for x. On the other hand, if I move to the e to the minus x to the other side, I can then draw e to the minus x. So e to the minus x goes through 1, right? And it blows up over here and asymptotes off to 0 out here. That's e to the minus x. Okay. Now, r minus x, these are straight lines with the slope of -1 at different values of r. So r, again, is my parameter, which I get to change, right? And so when r is equal to 0, I have that line. Now there's a line here. When r is equal to 1, it becomes tangent through here. And then if I have r equals any number bigger than that, we see that we have two intersections. Right? So for r greater than 1, we have two fixed points. There's two places where the r minus x intersects the e to the minus x line. At r equals 1, I have a tangency between the r minus x line and the e to the minus x line. And for r less than 1, I have no fixed points. So that means that I'm running into the situation where I have a saddle node bifurcation. So this system, x dot is r minus x minus e to the minus x, has a saddle node bifurcation when r is equal to 1. Because when r is equal to 1, this line moves up and hits in tangency the curve e to the minus x. And as I keep moving it up, I've got 2 fixed points because I have 2 intersections. Okay. So this is some version of a saddle node bifurcation. Good.
So the flow on this is going to be positive everywhere though, correct?
Well, okay, so let's think about what the flow is going to look like. So let's suppose that here's my e to the minus x. And let's suppose I do r equals 0. Here's my r equals 0. Right? So if r is 0, or any number for any r less than 1, I have no fixed points. X dot was r minus x minus e to the minus x. So in that case, r minus x is smaller. This is larger. So for any r less than 1, x dot is negative. So for any r less than 1, I have no fixed points and my flow is to the left.
So the flow, and I think I realized where my mistaken thinking was. On the previous equation that we did, it was when we crossed that x-axis, but the flow is determined by where they intersect. So
Well, okay, so the fixed points are determined by where they intersect.
right,
The
but
flow
like
is determined by the whole differential equation.
yeah,
And
but it
we're
doesn't have
figuring out
anything to
where
do
these
with
parts of the differential equation intersect to figure out where the fixed points are.
right.
So when r minus x is equal to e to the minus x, there's a fixed point. So for any r less than 1, there's no fixed points.
Yep.
So when r is equal to 1, there's 1 fixed point at the origin.
Yep.
For any r less than 1, there's no fixed points. Now, if r is minus x is less than e to the minus x, I've got a number minus another number that's positive. And so x dot's negative because whatever r minus x is, it's smaller than e to the negative x.
Okay.
And that minus sign that's right here is determining that I'm going to have a negative x dot. Now let me try to draw what would happen if I have, here's my e to the minus x, right? And here's my r minus x. And now here r is more than 1. So that means I've got a fixed point here and I've got a fixed point there. I've got 2 different x values for which they're going to be fixed points. And x dot is r minus x minus e to the minus x. Okay. So now I'm going to look at this as which of the blocks is bigger. Right? So in between, between these two blue points where I know there's fixed points. So the fixed points happen where there's an intersection. In between those 2 points, my flow is to the right. Because r minus x is the blue curve, the blue line, and the blue line is above e to the negative x. So whatever x value I have, the blue line in between these two fixed points, the blue line is above the black line. So the blue line minus the black line is a positive number.
That was where my mistake in like thinking was, because I thought it had to do with the axis, but then I realized it's
It's where these
Yeah.
curves are relative to each other. I'm
relative to each
subtracting
other,
these
not
two
the
curves
axis.
relative to each other. Yeah.
Right. Yeah.
So in between these two fixed points, the flow is to the right because the blue line is above the black line. On either of the other sides, the flow is to the left. Well, over here, yeah, no, they're both to the left, right? In the other cases, the flows are both to the left. So if I go over here to the far right-hand side, the black line is above the blue line. So the blue line minus the black line is a negative number. So that means the flow out here is to the left. And on the far side over here, the flow is also to the left because, again, the black line is above the blue line. And so when I had these two fixed points get born, this fixed point is positive, is stable rather, and this fixed point is unstable. So my stable fixed points are going to be to the right, and my unstable fixed points are going to be to the left. And so even though the differential equation would be very difficult to solve mathematically, if you told me an R value, I could tell you what it's going to do.
So I just want to be sure, when you're at the unstable equilibrium point, it's going to tend to go away from the unstable equilibrium point, right? But it
Right.
doesn't have like a greater tendency to go towards the stable one, right? It could just as equally well go like to the left as to the right.
Okay, so the fixed points. So if I have, so how should I think about this? I have x dot is f of x. So at f of x star equals 0, x dot is equal to 0, and I have no movement at all. So if I'm at a fixed point, whether it's stable or unstable, if I start exactly at that fixed point, I stay there. Okay. Now, this is where the linear stability analysis comes in, right? So let me say that I have x dot is f of x. And let me suppose that x star is a fixed point, such that f of x star is equal to 0. Okay, I'm going to define y to be x star plus delta. So y is the distance. Well, let me write. So if I rearrange this, right, it means that delta is y minus x star. Delta is the distance from the fixed point. Okay.
Okay.
Okay. So now, then is that the way I want to do it? Then y dot is equal to delta dot. Well, you know what? I'm sorry. Let me just use the letter X. I'm making things really complicated by introducing the letter Y. Let me let X be my variable. So X dot is equal to delta dot is equal to F of X star plus delta. Right. So if X is X star plus delta. So I'm basically going to define delta as the distance from the fixed point. Then X dot is equal to delta dot because X star is a constant. And X dot is equal to F of X, but F of X is now F of X plus delta. So that screams, do a Taylor series expansion on me. So delta dot would be F at X star plus F prime evaluated at X star times delta plus a half of F double prime evaluated at X star times delta squared, plus I could keep going. Does this make sense?
Good
Okay.
so far.
Now, if delta is small and F is continuous and smooth, which means that F in exists. So if all of the derivatives don't blow up, okay, then delta squared terms are smaller than the delta terms. And so approximately delta dot is approximately F prime at X star times delta. So let me call this thing lambda. All right, let me call lambda to be F prime evaluated at X star, right? So that's the derivative of my flow function, my ODE, evaluated at the fixed point. So now this is just a linear differential equation. So delta is some delta 0 e to the lambda t is the solution to the linear differential equation. And we see that if lambda is positive, I run away because delta grows. But if lambda is negative, I run towards the fixed point because delta goes to 0. So depending on the sign of the first derivative, I'm going to run away from or run towards the fixed points. And so when I look at my flow up here, I can think of it, you should always think of it locally. If I'm exactly on the fixed point, I don't move. But if I'm close to the fixed point, but just a little bit to the side, then what's happening at that fixed point drives my dynamics. So if I'm close to, but not exactly at a stable fixed point, I'm going to move towards that fixed point. If I'm close to, but not exactly at an unstable fixed point, I'm going to move away from the unstable fixed point. And because I'm in 1D, if I have an unstable fixed point to my left, I have to move to the right. And my only two options are to go to the right all the way to infinity or to stop at the stable fixed point. Right? So for instance, you can quickly convince yourself that stable fixed point here and a stable fixed point here, I suppose that there, could this happen?
There could be an unstable in the middle. All
right. So what's there can't happen.
Yeah.
Right. You would have to have an unstable fixed point in the middle because I'm trying to run towards this guy. I'm trying to run towards that guy. I'm trying to run towards that guy. I'm trying to run towards that guy. If there's not this unstable fixed point in the middle, then I couldn't have two stable fixed points next to each other in one dimension,
Right.
right? If I let myself have more than one dimension, then I can maybe get away with it because I could maybe get off the axis somehow, right? But even then, I'm not going to be able to get away with that, right? So because I'm trapped to move along this axis, if you've discovered in some region that there's an unstable fixed point here, and so the flow is this way, this flow on this side either goes to infinity or it goes to some stable fixed point. Those are the only two things it can do. And then, yeah, so if you're going to run away from an unstable fixed point, you either got to run it all the way to infinity or you got to run it towards a stable fixed point. You can't do anything else.
Okay, that makes sense. So
Maybe
I'm going to assume there's no, going off of that, I'm going to assume there's no just like individual unstable equilibrium points either.
Well, I mean, you could, so you could have one unstable fixed point.
Within it. Okay.
The flow looks like that. That's okay. That's okay.
Okay. But that's just,
Okay.
I don't know, the unstable one, it just seems like, because if you're going towards infinity and not towards a stable equilibrium or stable fixed
Yeah,
point.
but you can getting to infinity is okay.
Okay.
Coming from infinity is okay. So, I mean, just
Okay.
think about it this way, right? If I held up a positive electrical charge and I held it at the origin, and then I said, okay, I'm going to give you another positive charge and you're going to let it go. What would it do?
Well, they're going to repel away from each other.
It
Right?
would repel away from each other and go to infinity. It would look like that.
Ah, I see. Okay.
Right. So that's an okay thing to have happen. So
Thank you.
these are both okay things to happen. Or you can do this, that, this, that. That'd be okay. Right? Your flow would be towards, away. That's okay.
I think maybe I'm just biased towards infinity. Seems to
Yeah,
not
you're
like it.
okay with things going to infinity, but
I'm
or
just biased.
against infinity. Yeah.
You
all
just can't have any similar points next. Like you can't
Right.
have two unstable or two stable
yeah, you
without
can't
one or
have
the other in the middle.
that
Yeah.
without some stable thing in the middle. That would not be possible. Okay. All right. So we've done one of the types of 1D bifurcations. There's two more. We'll do the next two next week. Maybe I'll send out some little quick problems to work on. You try to do a couple of these problems. Basically, the idea is you think about how to plot it, you think about how to draw it, and you say, okay, what's going to be the stable fixed point? What's going to be the unstable fixed point? What's the linear stability analysis? So the fixed points happen where the x dot is equal to 0. Then whatever that function is, you take its derivative. The derivative at the fixed point tells you whether or not the point is stable or unstable, if you can't draw the function. Sound good?
Sounds good.
All right.
Quick
going
question
to-
if you have time.
Yeah, real quick though.
Are we gonna go into the Feigenbaum diagram at all?